Okay, here's the last part of the lecture covering projectile kinematics. Let's take a look immediately at an example of what happens when a projectile is launched from the ground at an angle. Let's go ahead and take a look at the problem associated with that, copy it down into your notes. Okay, let me read it to you. It's broken up into a number of parts. A projectile is launched from the ground at a 30-degree angle with a speed of 100 meters per second. In part A, we're asked to find the initial velocity components. Now notice, by the way, that I have the projectile kinematics equations from my previous portion of the lecture still written on the board. Of course, I'm going to use those equations as we move through this example. Okay, let's begin to set up part A of the problem. Okay, so we launch the projectile like so with an initial speed v0 that's given to us as 100 meters per second. Okay, right here are the components of the initial velocity vector. Right here is the horizontal component vx0. Here's the vertical component vy0. And then right here is the initial angle, theta0, equal to 30 degrees. So using these two expressions here and here, let's then use those expressions to find these initial components of the velocity vector. Okay, first of all, let's find vy0. Okay, so vy0 is going to be 100 meters per second multiplied by the sine of 30 degrees. So in degree mode on my calculator, I now plug in 100 times the sine of 30, and this comes out to be a total of 50 meters per second. Okay, and then we'll go ahead and find the horizontal component as well by plugging in the following: 100 times the cosine of 30 degrees. Okay, so 100 meters per second times the cosine of 30 degrees, and this works out to be about 86.6 meters per second. Okay, so we'll use these components now as we begin to move through the remainder of the example. Okay, in part B, it says how much time is necessary for the object to reach its maximum height. Okay, so the projectile begins to move through its path like so, and then right here at this instant, the object is at its maximum height. Now, at that instant, the velocity vector of the projectile is going to be entirely horizontal. The vertical component of that velocity vector is 0 when the object reaches its maximum height at this instant in time. So right here is that velocity vector. We're just going to label it as v, and let's note that the vertical component of it, v sub y, is equal to 0. We're actually going to calculate here two things as we move through parts B and C of the problem. Parts B and C of the problem are going to go together. We're going to calculate the amount of time necessary for this to occur, and then we're also going to calculate right here the final vertical position y. This is the maximum height. Incidentally, by the way, to make a comparison for later on in the problem, we're also going to calculate right here the horizontal displacement x, like so. This will be unknown as well. Incidentally, by the way, when we do start from the ground, let's just immediately say that the initial position x0 horizontally and y0 vertically is equal to 0. So let's write that down before we proceed. Like so. Okay, now let's find the total time t. In order to find the total time t, we're going to use the velocity equation for the vertical direction. The reason why is because when you reach the top of the trajectory, v sub y, as we noted earlier, is equal to 0. So let's go ahead and use this expression right here and plug into it. V sub y is equal to 0. Okay, I'll do that over here like so. And now here on the right-hand side of the expression, the only thing that's unknown is the time t, which we can now solve for. That will give us the time from here to here. That's what's being asked for. So let's go ahead and algebraically move the gt to the other side, like so, and then divide the g term to the denominator on the right-hand side to get the time t by itself, like so, and now I plug in. So I plug in here into the numerator of the expression, 50 meters per second, and then divide by 9.8 meters per second squared. Okay, so 50 divided by 9.8, and that works out to be 5.1 seconds. So it takes 5.1 seconds for the object to go from here to here. And now that I have that time, let's go ahead and find the maximum height y by just using right here the vertical position equation. On the right-hand side of the expression, everything is now known. The initial vertical position y0 is equal to 0, and then we'll have plus 50 times 5.1 minus 1/2 times 9.8 times 5.1 squared. So let's just go ahead and plug in everything and calculate y. All right, so doing so in my calculator, So 50 times 5.1 minus 1/2 times 9.8 times 5.1 squared. This works out to be a total height of about 127.55 meters. Okay, then I'm also going to calculate here the horizontal displacement x, because we'll eventually make a comparison when we get later on into the problem into parts D and E. Okay, in order to calculate x, let's just look at the horizontal position equation. And now, once again, here on the right-hand side of the expression, everything is known. So I'm going to plug in 0 plus 86.6 meters per second multiplied by 5.1 seconds. Okay, so 86.6 times 5.1, and that comes out to be about 441.7 meters. Okay, now let's move on to the remainder of the example in parts D and E, and as we do, we're going to begin to see some symmetry for parts D and E. Now we want to see what happens when the object returns to the ground. Okay, so parts D and E are going to go together. We're going to once again launch like so with the initial speed. Here are the initial components of the velocity vector, Vx naught and Vy naught. Once again, right here is the initial angle theta naught. They were launching from the ground once again, that's the origin, so both x naught and y naught are 0. But now we take a look at the entire path, like so. And when we take a look at the entire path, this then means that vertically, the final position of y is equal to 0 because we return down to the ground. And then here's what we're asked to calculate in parts D and E of the problem. We're asked to calculate the total time t, and also right here, this horizontal displacement x when the object returns to the ground. This is specifically part E of the problem. This is what is referred to as the range. The range is the horizontal displacement of the projectile when it returns to its original height. Okay, now before I calculate the total time t and the range x, let's see if intuitively we could figure out what the answers should be already. Take a look at part A of the problem. Keep in mind that in part A of the problem, the time necessary for the object to reach its maximum height was 5.1 seconds. That was basically the time from here to here. So then therefore, using a little bit of symmetry, what do you suppose the total time is going to be from here back here down to the ground? If you are intuitively guessing 10.2 seconds, you are in fact correct. The reason for that is because the parabola, or rather, the projectile's trajectory is in fact a parabola, which is a specific type of curve, a conic section that you will study a little bit later on in mathematics if you've not seen it already. For those of you that have seen parabolas in mathematics already, yes, the trajectory that is traced out by a projectile is in fact a parabola. But we do have to find that time. So let's go ahead and calculate that time in the following way. We're going to note right here that both the final and initial vertical positions are equal to 0. So let's go up to the vertical position equation where we're going to set both y and y naught equal to 0. When I do, the equation simplifies to become the following. And now in this expression, the time t is the only unknown, and here's then how I'm going to algebraically solve for it. Because this is 0 here on the left-hand side of the expression, I could actually safely cancel out a t here from each term like so. And then the total time t that remains here, it's what's being asked for in this portion of the problem, and now we can go ahead and solve for it. So let's take this 1/2 gt and move it to the other side. And now I'm going to cross multiply the 2 over to the other side and divide the g over to the other side to get the time t by itself. And when I do, that then yields the following expression. This expression here came from the vertical position equation. Compare this expression, however, to this expression here earlier for part A of the problem that came from the vertical velocity equation. Notice that this expression here is twice as much as this. So then therefore, yes, the total time is 10.2 seconds. So then therefore, the time necessary to go up, if you will, is 5.1 seconds. The time necessary to come back down is 5.1 seconds as well. Therefore, the total time is 10.2 seconds. Okay, and then lastly, for part E, let's go ahead and calculate the range. In order to do so, we're going to use this expression here. The only difference, however, from when we used this expression earlier in part A of the problem to now here in part B of the problem is that the time t has doubled. Keep in mind that x naught is equal to 0. So then therefore, if the time t has doubled, this then means that the value of x has doubled as well. That should be no surprise at this point due to the symmetry of the parabola associated with the projectile's path. So suffice it to say, the value of x here is going to be twice this value here. If you double that value, it comes out to be 883 or so, 0.7 meters, like that, okay? All right, this is as far as we go here in Conceptual Physics AB for the mathematics associated with the kinematics of a projectile.